So here in 6.2 we want to look at properties of our sampling distribution. In the last section we actually created a sampling distribution for the sample mean. First I want to talk about point estimators of a population parameter. So those are either a rule or a formula which is going to tell us how to compute a single number here that estimates our population parameter. Now that estimate could be biased, and that's when the mean of the sampling distribution here is not equal to the population parameter. And it's unbiased if the mean of the sampling distribution does equal the population parameter. So here's a picture of an unbiased sampling distribution, an unbiased estimate. So here's our population parameter, and it is at the mean of the sampling distribution for this sample statistic. Now over here, this is a biased sample statistic. So here's our population parameter, but over here is the mean of our distribution. So this difference here is bias in the estimate. So bias is one thing that we want to consider. We always want an unbiased estimator. Also, we want to consider the spread of the distribution and how that makes the estimate better. So here we've got two sampling distributions. So this is for statistic A and statistic B, and we can see that the sampling distribution here for statistic A has a much smaller standard deviation. So we ask here which estimate is better, and it's going to be A, because if we have less variation, that means a more consistent estimate. So if you have two sampling distributions and one has less variation, if they're both unbiased, you want the one with less variation. And then the standard deviation, or the measure of variation for sampling distribution, is called the standard error of the statistic. So that's our standard deviation of the sampling distribution for that statistic. Now recall that for any random variable, the variance, sigma squared, is the sum of x minus mu squared times probability of x. And so the standard deviation is the square root of that quantity. So, and that works for any random variable, so it would work for a sampling distribution as well. Or the test statistic, the statistic here that is the random variable. The sample statistic that generates sample means that form the random variable. So let's look at an example here. We're given a following probability distribution for a random variable x. So it's got values of 0, 1, 2 in equal likelihood. They first want us to find the mean of that sampling distribution, which is the sum of x times probability of x. So 0 times 1/3 is 0, 1 times 1/3 is 1/3, and 2 times 1/3 is 2/3. And we add those up, we get 3/3 or 1. So the mean of that distribution, or expected value of the random variable, is 1. And then if we find the means of all possible samples of size 3 and find their probabilities, we get a sampling distribution for the sample mean, x bar, for size 3. Well, we not only could do that with means, we could do it with medians. So if we find the median now of all samples of size 3 and find their probabilities, we get the sampling distribution of the sample median. So it's a different sampling distribution because it's a different statistic that we're looking at. We're looking at median instead of mean. Now, if we do that in this case, our possible x bar values here, so this is the x bar values for the sample mean, and this is the probability of each one of those values. So this is the sampling distribution for sample mean. And then if you multiply x bar times probability of x bar, that's this column, you add them up, you get 1. So notice here that the mean of the sampling distribution is equal to the mean of the parent distribution. This is our theta, that's our population parameter. So we can see that the sampling distribution for the sample mean is an unbiased, the estimate is unbiased because those two means are equal. Now if we do medians here, 0, 1, and 2 are the only values for the median. These are the probabilities that they fall in. And then if you multiply m times probability of m and add those up, you also get 1. So that's also an unbiased estimate. So which one is better? Well, we look at the standard deviation. So if we do the standard deviation of the sample mean distribution, we get 0.47. If we do sigma sub m, the standard deviation for the sampling distribution for the median, we get 0.72. So which estimate is better? Well, it's going to be the sample mean because the standard deviation is less. So sample mean, sigma x bar is less than sigma m. So the standard deviation or the standard error is actually the correct terminology. So while the sample mean and the sample median are both unbiased estimators, the sample mean has a smaller standard deviation, which means it's going to be a more consistent estimate. So if they ask you in the homework, you have two estimators and you want to know which one's better and they're both unbiased, pick the one with the smaller standard deviation.